Hi everyone, this is Srikanth as Assistant Professor of Triple Department. In this session, I am going to discuss the H parameter model for common collector amplifier. In this configuration, the base terminal of the transistor serves as the input and the emitter terminal is the output. Here we are making the collector terminal as the common. So base will be serving as the input terminal and emitter will be working like a output terminal. The input applied between base and collector and the output is taken between the emitter and collector. In common collector configuration, the collector terminal is grounded. So the common collector configuration is also known as grounded collector configuration. This is the common circuit common collector configuration circuit. Here the base to collector junction will be forward bias and whereas emitter to collector junction will be a reverse bias. Here the common collector configuration is also referred to as emitter follower, voltage follower, common collector amplifier, CC amplifier or CC configuration. This configuration is mostly used as a voltage buffer. Here the input supply between the base and collector is denoted with VBC and the output voltage between the collector and emitter is taken as VEC. Here the IB and IE are the base current and emitter current, and this amplifier has high input impedance and low output impedance, and it has low voltage gain and high current gain. Here the power gain of the common collector amplifier is medium because it has low voltage gain, it has high current gain. The power gain will be voltage into current, so it has medium power gain. And to fully describe the behavior of transistor with CC configuration, we need two set of characteristics. One is input characteristics and the other is output characteristics. The input characteristics is between the VBC and IB. This is the input characteristics, VBC versus the base current. When EC is at some constant value, we are going to get the characteristics like this. The output characteristic is between IE versus VEC when IB value is kept constant. Here is the IB value when we keep at 0 microamperes. IE versus VEC values will be having with different base current. We are going to have different the characteristics between IE versus VEC because when the base current increases, the emitter current is also increases. In common collector configuration, if the input or base current is 0, then the output current is also 0. As a result, no current flows through the transistor. So transistor will be in the cutoff region. When there is no base current in the transistor, there is no output current or no current flows through the transistor. So that region is called cutoff region. If the base current is slightly increased, then the output current or emitter current is also increases. So the transistors falls into the active region. If the base current is heavily increased, then the current flowing through the transistor also heavily increases. As a result, the transistor will falls into the saturation region. Now we'll go with the transistor parameters. The first one is dynamic input resistance. The dynamic input resistance is nothing but the name itself says it is the dynamic resistance when there is a change in voltage for, for a different values of VBC. What are the corresponding IB we are getting in the input characteristics? That changes we have to note down, and Ri, that is input impedance, is equals to delta VBC by delta IB when VEC value is constant. Here the input resistance of common collector amplifier is very high because IB value is very less. Always the base current value will be in terms of microamperes, so the input impedance will be high. And dynamic output resistance, when there is a change in voltage corresponding to the change in output current by keeping IB constant, then that is called a the ratio of change in voltage to the change in output current is equals to the output resistance R naught, where R naught is equals to delta VEC by delta IE, where IB is kept constant. Current amplification factor. The current amplification factor is defined as the ratio of change in output current or emitter current to the change in input current or base current. It is expressed by gamma, where gamma is equals to delta E by delta IB. The current gain of common collector amplifier is high. Now voltage divider network, which the voltage divider equation V output is equals to VCC into R2 by R1 plus R2. From this, base voltage is equals to VCC into R2 by R1 plus R2. Here V output is equals to V input into RE by RE dash plus RE, where AB is equals to V output by V input, which is equals to IE into RE by IE into RE dash plus RE. If IE will get cancelled, here RE dash is much greater than RE. RE is much greater than RE dash, that is leakage current, leakage resistance. So, which is approximately equals to RE. AV is equals to V output by V input, which is approximately 1. The common collector amplifier example. The common collector amplifier is constructed using NPN bipolar transistor and a voltage divider biasing network. If R1 is equals to 5 kilo ohms and R2 is equals to 6 kilo ohms, and the supply voltage is 12 volts. Calculate the values of VB, VC, VE and the emitter current IE, the internal resistance RE dash and amplifier voltage gain AV when the load resistance of 4 kilo ohms is used. Also draw the final circuit corresponding to the characteristic curve with load line. Here this is 5 5.6 kilo ohms, that is 5600 ohms. Here it is 6800 ohms. Here it is 4700 ohms. The R1 value is 5600 ohms. R2 value is 6800 ohms. And load resistance is 4700 ohms. Here I is equals to VCC by R1 plus R2, 12 by 5600 plus 6800, that is equals to 968 microamperes. Where VB is equals to I into R2, that is 968 into 10 to the power of minus 6 into 6800, and this value is 6.5 volts. The collector voltage VC, as there is no collector load resistance, the transistor's collector terminal is connected directly to the DC supply rail. So VC is equals to VCC, which is equals to 12 volts. Now emitter biasing voltage VE is equals to VB minus VB. Here 6.5 minus 0.7, that is 5.8 volts. Thus VCE offset is equals to VCC minus VE, that is 12 minus 5.8, that is equals to 6.2 volts. Emitter current is equals to VE by RE, that is 5.8 by 4700, that is 0.00123, that is 1.23 milliamperes. And AC emitter resistance RE dash is equals to 25 millivolts by IE, that is 25 millivolts by 1.23 milliamperes, that is 20.3 ohms. Voltage gain AV is equals to small re by small re plus RE, that is 4700 by 20.3 plus 4700, that is 0.996, which is approximately equals to 99.6%. For AC analysis of the circuit, capacitors are shorted and VCC is shorted. Thus, the equivalent circuit is given as shown with the biasing and voltages given as, where RB is equals to R1 in parallel with R2, RB is equals to R1 is in parallel with R2, and RE is equals to RE is in parallel with RL, where beta is equals to IC by IB, where from this IC is equals to beta into IB, where IE is equals to IC is equals to beta IB, where V input is equals to VB is equals to VBE plus V. The input impedance of common collector configuration looking into the base is given as Z input is equals to R base is in parallel with Z base, where Z base is equals to VB by IB, but VB is equals to IE into RE plus RE dash, where IE is equals to IC plus IB and IC is equals to beta into IB, where Z base is equals to VB by IB, that is equals to IE into RE plus RE dash by IB, which is equals to IC plus IB by IB into RE plus RE dash. From this we'll get it as beta plus 1 into RE plus RE dash, where Z base is equals to beta into RE plus RE dash, and common collector amplifier input impedance Z input is equals to R bias into Z base, where R bias is equals to R1 is in parallel with R2, where Z input is equals to RB is in parallel with beta into RE plus RE dash. Now H parameter model for common collector amplifier. Here the collector gain, current gain from the above circuit, where IL is equals to 1 plus HFE into IB, where current gain AI is equals to IL by IB. AI is equals to IL by IB, which is equals to 1 plus HFE. This is the current gain which we are going to get, and the input resistance Ri from the figure VB is equals to IB into HIE plus 1 plus HFE into IB whole into RL, where Ri input impedance is equals to VB by IB, that is equals to HIE plus 1 plus HFE into RL, 1 plus HFE into RL. And the voltage gain from above figure VC is equals to 1 plus HFE into IB into RL, where AV is equals to VC by VB, which is equals to 1 plus HFE into IB into RL by IB into HIE plus 1 plus HFE into IB into RL, where IB will get cancelled. You will get 1 minus HIE by HIE plus 1 plus HFE into RL, that is equals to 1 minus HIE by RL. The output resistance from figure 5, the open circuit output voltage, which is equals to Vs. The short circuit output current I is equals to 1 plus HFE into IB, that is equals to 1 plus HFE into Vs by HIE plus Rs. Hence the output impedance R0 is equals to open circuit output voltage by short circuit output current, that is equals to HIE plus Rs by 1 plus HFE, where output terminal impedance is equals to R0 is in parallel with RL. And these are the expressions for H parameter model equations in common emitter, common base and common collector configuration, where quantity current gain is equals to minus HFE in the common emitter configuration, and common base configuration HFE by 1 plus HFE, where in common collector configuration that value is 1 plus HFE, and input impedance is equals to HIE, and in the CE configuration, in CB configuration HIE by 1 plus HFE, and in CC configuration HIE plus 1 plus HFE into RL, where the voltage gain value AV is equals to HFE into RL by HIE and HFE into RL by RE, which is equals, this is in the common base configuration, and in common collector configuration 1 minus HIE by RI. And the output impedance is infinite for common emitter and common base configurations, whereas for common collector configuration HIE plus RS by 1 plus HFE, where resistance at the output terminal is RL in the CE configuration, in CB RL, and in common collector R0 is in parallel with RL. In this session, we have discussed the H parameter model of common collector amplifier circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.